Okay. Good afternoon and welcome back. No bell work on your computer today. So actually your opening activity here, I'm going to show you a short little video. Everybody got a ruler and a piece of paper that Oren gave them? Yes. I'll tell you what that piece of paper is in just a second. But first we're going to watch a little video here. So here we go. Pay attention. Okay, Katie's confused. Somebody tell her what just happened.
Well, Brian was counterfeiting money for him.
He was counterfeiting money? He was making copies of his dollar bill. So when he did it the very first time, we'll watch it again here. Let me fast forward a little bit. Okay, here's the first time. Now this part coming up is key because he doesn't just push copy, he does what? So when he pushes go, the copy is going to come out bigger or smaller than the original dollar bill? Smaller. How much smaller? 75% of the original, right? So when he takes that first piece of paper, what's going to happen the second time? It's going to be smaller not only than the original dollar bill, but smaller than the piece of paper that's on the glass, right? Okay, so, and he's going to keep doing that over and over again. So what I would like you to do, you have in front of you, I would have brought dollar bills for everybody. I only carry hundreds, so that's why, no, I'm just kidding. I couldn't afford to bring you guys dollar bills. So I gave you a piece of paper that is exactly the size of a dollar bill, the outline. Okay? A dollar bill, American dollar bill, is 156 millimeters by 66 millimeters roughly. I want you to pretend that you don't need to cut it out. You can just leave it there. I want you to pretend that that's your dollar bill. And I want you to pretend that you did what he did on the video 9 times. 9 times. Here's what I want you to do. Once you've thought about that happening 9 times, what I would like you to do, and it says keep the dollar pinned to this corner. I want you to just sketch for me with a pencil. How large do you think your dollar bill would print out on the 9th copy if you did that 9 times? So if you think it's going to be this big, then it's going to be that big. If you think it's going to be this big, then it's going to be that big. You need to determine, just draw in, how big do you think it's going to be? Go ahead. You can guess. You can do calculations. You can use your calculator. You can use your ruler. 9 times is what we're doing. 9 copies. when you have something drawn of how big you think it's going to be, flag me down so I can look at it. See some of you doing some math work here. That's what you think your final size is going to look like? Correct. That one there, okay.
I was waiting for it.
So now I want you to ask yourself, do you have any mathematical reason to think that it's going to be the size that you drew? Or are you just guessing at it and waiting for Jamie to tell you the answer? You just answered correct to an or question. So is this after 1 and after 2?
Yeah.
So I see where you're going. You're going to do 3, 4, 5, 6, 7, 8, 9. It's going to take you forever.
It's going to take me forever.
Can you cut to the chase? Now that you know what you're doing, is there a way for you to do it faster?
Maybe.
Maybe?
Maybe.
Is this after once?
Yep.
After twice?
Mm-hmm.
So you're going to do 3, 4, 5. It's going to take you forever, right? Is there a way to do this faster so that you don't have to draw out each one? I'm not interested in seeing all 9 of them. I just want to know what the last one's going to look like. What's it going to look like after we do this copy 9 times? You don't have to show me 8, 7, 6, 5, 4, 3, or 2, or 1. Okay.
You drew it. Why are you yelling at me?
Yeah. Because I took these numbers times 0.75.
So this number you took times
0.75.
to get that.
Yep.
And then you're going to take him times
0.75.
to get that.
Yeah.
But we could do this with... I like your thinking. Now, we could do this without drawing it each time, couldn't we?
Probably.
Yeah.
There's one of those tick marks. Okay, I go through it. I have my knowledge of it. It's 25% off of the 25% off.
Mm-hmm. So
There's a button on your calendar.
oh, you think so?
I think so.
You're right. If you take 25% off, you're going to keep 75%, right? So you're correct, but by taking 25% off, you're probably adding one extra step every time. Whereas, so instead of thinking on what I'm going to take off, think about what I'm going to keep. The 75, right? Then you don't have to do the subtraction every time. You just times 75% and you're right to where you want to be.
Jack's like, ooh, I got a calculator. Now let's go.
You did it. Give me mine. I did it.
Okay, I'm going to give you a few more seconds to come up with something. Did you guys draw anything in?
Yeah, kind of. But we just
Like
did
that?
plug and chug.
Yeah. Uh-huh. Okay. If you don't have a final answer yet, I want you to just stop calculating and take an absolute guess at it. Guess what you think it's going to look like. Is that your final right there, Alex? Okay. Okay. I'm going to show you the answer visually. Then we'll talk about it, how we can actually compute it mathematically. So, give me a second here. Wrong math course. 6. Nope. Yikes.
You don't just tell someone like you're...
Okay, you guys ready? Here we go. Here's the original. Count along now. That was 1. We're going to do 9. There's 2. There's 3.
I think it might be a little smaller than I thought.
4. This one is 5. This one is 6. There's 7. There's 8. And there is 9. Now notice we get a nice picture of this when he shuts the lights off. You can kind of see the outline of each one. And this was what a lot of you were doing. A lot of you calculated, okay, what's it going to look like after 1? And you drew this in, right here. And he said, what's it going to look like after 2? And you drew that in. After 3, after 4, after 5, which is a good strategy. It's going to be a nice picture. It's going to produce exactly what this is going to produce. Except some of you found like, oh my gosh, this is taking forever. Like what happens if I would have told you what's it going to look like after 19 or 27 or 300? Like you would never want to draw all of them out, right? Okay? So we'll talk about this in a second, but let me pose one other question for you first. He did it 9 times and we got down to this, right? How many times would you have to do this before your dollar is down to nothing? It's 0. There's nothing left anymore.
I don't think you can do that.
Katie says you can't do it. Do you guys agree with that? Regardless of how tiny it gets, even if it's so small that our human eyes can't see it, do you guys agree that 75% of something is still something? Right? So there's lots of different examples of this that people have talked about. There's one called like Zeno's paradox. So that one says that I can, if I'm going to walk towards the wall, I can continue walking towards the wall, and every time I take a step, I will move closer and closer to that wall, and I can walk forever and never get there. Does that make sense? I can walk forever, but never get there. How would I do it?
Well, so you can't get into the wall. So.
Let's say I'm about 12 feet away right now from the wall. You guys agree? If I'm walking right towards the door frame there? What happens if I walked halfway there? Then I'd be at 6 feet, right? What happens if I walked halfway there again? Then I would be at 3 feet. What happens if I walked halfway there again? 1.5. Halfway there again, 0.75. Halfway there again, half of 0.75, whatever decimal that comes out to be, right? Halfway again, halfway again. What happens if I keep walking half of the remaining distance and I keep doing that forever? Will I ever get to the wall? No. But am I actually stopping? Or am I continuing to move that way forever? I am moving that way forever. It's just that I'm moving so much that it's humanly impossible to do it. But theoretically, it can be done. It just, the decimal gets smaller and smaller and smaller, but we know decimals go on forever, right? So the same thing with this. Half of a distance is always some distance. You're never going to take a distance, cut it in half, and get 0. That's impossible, right? So 75% of a dollar bill is always going to be something. All the way till the point where we can't split the atom, right? For those of you that are science majors. So, some of you were on this pace of doing this. And some of you were, I want to say, Noah, you guys back there said, well, we got something, but we just plugged and chugged it the whole way. Like, enter in the calculator, enter in your calculator. So, what happens if I started with that original? That's not what I wanted. Here's my original dollar, right? Let's just look at the 156. We'll talk about the height later. Let's just look at the length, okay? It starts out at 156. So if I want to calculate my new length after one copy, after only one copy, Jordan, I think you did this. 156 times what? Do you guys agree that my new width, I could take 156 times 0.75, and my new width, if I just did this one time, would be 117? I could do the same thing for the 66, and I'd have both, right? But we'll just look at the 156 for now. So that gets me after 1. Now what am I going to do if I want to get to my second copy?
Multiply it again.
Take this same number times 0.75, and now I'm at 87.75. And some of you were doing this, right? What happens if I want to do it again? Times 0.75 again. Now there's a trick for those of you that have a TI calculator. Once you do something twice in a row, if you just hit enter, it does it for you. It knows what you wanted it to do. So that's after 3. You guys agree I've done it 3 times? If I do it again, 4, 5, 6, 7, 8, 9. Oh, 9 is where we were supposed to stop, right? So after 9, how wide was your dollar? I got 11.71. What's my label? Millimeters. How many of you tried to draw it out at 11.71 millimeters? A few of you? Good. So a few of you knew what you were doing there. Okay? How could I have done that so I don't have to do it times 0.75 in my calculator 9 times? I could have just started with, what was it, 56? How do I do this on my calculator? Jack, you're like, there must be a button for this.
I don't have a TI calculator. I have this old, goofy blue one I found on the floor. So there's a button that I can just, enter the numbers into and it does it for me, but it's not like.
What button is he referring to? Almost every calculator is going to have this button on it. Nobody knows what I'm talking about here? We want to take it times 0.75. How many times are we going to take it times 0.75? 9 times. How do we do repeated multiplication in math? Holy 6th grade people. How do we do repeated multiplication in math? It's called to the power. It's called an exponent, right? If I want to take something times 0.75 over and over and over and over and over again, I can just take it times 0.75 to some exponent, to some power, right? How many times do I want to do it? 9 times. So on my TI, I'm going to use the caret button. Some of you might have a y to the x button. It's an exponent button on your calculator. I'm going to take 156 times 0.75. How many times am I going to do it? I'm going to do it 9 times. And if I hit enter, notice I get right to my 9th one. I don't have to do it 9 individual times. So why do we have exponents in math? It's really, really simple. It's a shortcut for when we want to multiply something times a number over and over and over and over and over again, but we want to save time. Hence, the exponent is a time saver. You guys comfortable with that? So that was the length. What about the height of the dollar bill? I think it was 66, right? What are we going to do? We're going to take 66. We're going to take it times 0.75. How many times are we going to do it? 9 times. Should have been a little less than 5 millimeters tall. So for those of you that got about 11.7 and about 4.95, and that's what you drew in, then you know what you're doing. Okay? Not too bad. Comments or questions on that? Let's do one other activity. Go to Blackboard for me. Underneath Desmos, Avi and Benita's repair shop. You guys see that? It's another Desmos activity. Read the directions and get started. And we'll see how it turns out. Avi and Benita's repair shop is what it's called. each day you get to choose a different payment rule. So you can change on day 2 or day 3 if you want. Each day you show up at work, you get to decide what rule you're going to use. If you guys look at the screen, you're going to find out that Avi's not getting any love on step 2. You guys are all with Benita so far. And then in step 3, you're going to find out if you were correct or not. Nobody wants to vote for Avi on day 2? So when you're on step 3, you might want to use a calculator. If you're clever and you know how to use your calculator quickly, that'll cut some time off. Or maybe you can just do the math in your head. As you're finishing up step 3, which most of you are, Avi came up way short, right? Like it wasn't even close. So Benita was definitely the right answer for that one. So far on day 5, we have some of you choosing Avi and we have some of you choosing Bonita. So we have some disagreement going on there, which is good. What that means is some of you are correct and some of you are not. Step 2 was too easy. This one's a little tougher. I'm going to pause you for a second. Here are 4 sample responses from step 4. It said, describe what the graphs look like and what's going on. What's similar, what's different. It says they're different. Bonita's goes up and Avi stays, I think this person meant to say horizontal. They're both increasing. Is Avi's staying horizontal? Oh, I forget who's who again. Which one does the $1,000 or the $100? Avi? Bonita. Okay, so Bonita's is going up like this, right? Mm-hmm. Is Avi's staying horizontal? Is it moving up? It is. It's to the naked eye, it looks horizontal. Because it's such a small amount that it's moving up that it looks like it's a flat line, right? They aren't very closely related. Bonita has a greater slope than Avi. Do you guys agree that the slope of Bonita's is greater? At this point. Yeah, and slope is a very precise word. Slope is a line, right? We use the word slope of a line. So, talk about that a little bit. Let me come back to this one. They are both linear. What do you think? Do they both make a straight line? I don't think they do. I think Bonita's is a straight line. The blue one is a straight line. Is the red one a straight line? No. So I would say they're not both linear. Okay, check out this person. Avi's rule is an exponential function of days. Bonita's rule is a linear growth curve. Both will eventually pay similarly. Bonita will pay more right away, but less in the future. Person sounds like maybe they know what they're talking about. Okay, I'm going to unpause you. Take a look at the current vote. 12 of you are with Avi, 8 of you are with Bonita, so we're still split. I'm going to give you a little bit of a hint on step 6. When you guys are filling in the table, you can punch it in your calculator if you want. You can also use the computer as a calculator. So let's say I wanted to take some number times some number, like 75.6 times 81.4. I can just hit enter and it'll calculate it for me. So if you want to do math right inside of the box, you don't even need your calculator. Just type it right into your keyboard. Step 2 once for me. I think you kind of missed your, yeah. So, it's not going up 2 cents every day. What's that number going to be? You missed the pattern. 1 cent to 2 cents is double. Yeah. 2 to 4 is double. So 4 to 8. So now go to your next step. Your step 3.
Oh.
Right there. After 8, it's going to be what? There you go. Yep. So you had the wrong pattern. That'll change everything now, by the way. Riley, let me see your step 3. Maybe you fixed it already. So way back on step 3. So it's not going up 2 cents, 2 cents, 2 cents, 2 cents, 2 cents. It's going from 1 cent to 2 cents. It's double. 2 to 4 is double.
Okay.
4 to 8 is double.
Okay.
There you go.
Thank you.
That'll change everything for you now. Yep. most of you are looking good on step 6 with completing the table. Some of you are off. If you look at step 6 here, check mark means you got the right table. X means you're wrong. So you did something wrong. Double check your math on the table. Do you guys see what your fake name is? Oh, so you guys can tell who's who up there, huh? Or you can tell who you are anyways, right?
Yeah.
Okay, so go ahead and look for your name. If you see an X on step 6, you got something wrong, Victor. Marion, poor L something. Pythagoras, you're wrong. Check your step 6. A dot means you're still working on it. It means you didn't submit it. It might just be off the screen. Is it down here? If I'm not mistaken, it should be, what, $5,242.88?
Yeah.
$5,242.88 for, I get my names mixed up, for AV, right? Bonita's should be easy. You don't need a calculator for that. You can just do it in your head, right? So as you guys are moving on here, I still have, it looks like AV has 18 votes and Bonita still has 5. Back on step 5. If you're trying to find your mistake, here's what a correct one looks like. I'll leave it up on the screen here. This is Gaspard's. So this is where you want to be a little bit clever with your calculator. Notice our table is jumping from 13 all the way to 20. If you want, you could fill in 14, 15, 16, 17, 18, 19, but we don't want to work that hard. We want to be efficient, right? So we should just be able to cut to the chase, right? In one line in your calculator, you should be able to do this. In fact, you could start all the way up at, if we showed the rest of the table, day 8, 7, 6, blah, 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 where did we start? 1 cent? So can you make it from day 1 all the way down to day 20 without punching all the others in? You should be able to. What are we going to start with? 1 cent. We're going to take it times 2. How many times? It's not 20. 19, because 1 cent is the first day. So to get to day 2 would be times 1, day 3 would be times 2. So we're going to do it 19 times, right? So you should be able to get to this number without even filling in the rest. That's the power of exponents. It helps us be efficient so we don't have to do repeated multiplication over and over and over again. So what happened on day 20? Who's the winner? It's Avi, right? Because what did Benita come up with? Was it only 2,000? Yeah, it was $100 a day, right? So obviously you'd rather have $5,200 as opposed to 2,000, right? Now, thus far we've only talked about how much you get paid each day, right? What about the cumulative? If you get to add day 1 plus day 2 plus day 3 plus day 4, that's a different question, right? And that actually comes into play now at those of you that are on step 9. It says instead of letting her decide each day which way she'd like to get paid, she has to make a decision with either Avi's way or Benita's way from day 1 and got to stick with it. So they're changing it up on you on the last step. So somewhere in there's going to be a cutoff point where Avi's plan is going to be better than Benita's plan, right? Like we found out way back on step 2 or 3, if you're only going to work there for 10 days, whose rule do you want to go with? Benita's going to be way better, right? Like $1,000 to 5. Okay? Where's it going to finally pass? If you're going to work there for day 18, actually it could even possibly be day 17 if you add all of them up. You'd have to do a little bit more extended math on that. But the moral of the story is, if you look at all these graphs, one of them is a straight line and one of them is exponential. And that's what we're covering now, is exponential. So we got 4 minutes left. I want to show you just a little summary here. This is what we've done since we started chapter 3 or whatever. We talked about lines for a long time. We talked about quadratics or parabolas for a long time. We talked about a little bit about polynomials, degree 3 and 4, like the volume of the paper box. That was a 3rd degree polynomial. We talked about rational. 1 day we spent on rational. You guys did the worksheet with the company that makes shoes, right? Now we're going to spend the rest of our time on exponential and logarithmic functions. And that's what chapter are we on now? Chapter 6. So here's just a couple more real-life examples. Have you guys ever heard the term the snowball effect? This happened, and this happened, and this happened, and the whole thing snowballed on me. You guys have heard that before? Has anybody, if you grew up in North Dakota, you've probably done this before. When you make a snowball, what happens when you got the good, wet, sticky snow, which we might be getting tomorrow? What the heck? Shh. You start with a snowball this big, and you roll it a little bit, and pretty soon it's this big, and you roll it one more time, and pretty soon you can't even lift it, right? It grows exponentially because the bigger the snowball is, the more you roll it in wet, heavy snow, the faster it grows. Maybe you guys have heard this term. The rich get richer. Why do rich people get richer? They keep making money. How? By investing it. Because if you have a whole truckload of money and you invest it at a certain interest rate, it's going to grow exponentially. Okay? So, last thing we're going to talk about here. I wrote it up on the board. This is the basic form of an exponential equation. Very, very basic. We can do some different, transformations and stuff on this. But if we have some original amount, so for the length of the dollar bill, the original amount was 156 millimeters, right? For the daily pay for Avi, the original amount was 1 cent, 0.01, right? Somehow we start with an original amount. Then we take that original amount and we multiply it times some number. For the dollar bill, we multiplied it times 0.75. For AV, we multiplied it times 2. Notice one of them went down and the other one went up, right? The dollar bill got smaller and smaller and smaller and smaller, but AV's daily pay got bigger and bigger and bigger and bigger, right? So let me ask you this. What happens if the multiplier was the number 1? And we took some amount and we multiplied it times 1 over and over and over and over and over and over again? It would be the same thing. So if I started with a dollar bill and he did 100%, which would be times 1, and made 9 copies, the 9th copy would still be exactly the same size as the original. Because you guys know if you take a number times 1 over and over and over and over and over again, you're still at the same darn number, right? What happens if you take something times a number larger than 1? It's gonna grow. What happens if you take it times a number smaller than 1? It's gonna decrease. So 1 is like our break-even number, right? Larger than 1 growth? Okay. And then how many times are we going to multiply that number? That's our exponent. So for AV, it was 19 times, because there was 19 days in which she doubled the pay. For the dollar bill, it was 9 times. For something else, it'll be some other number, right? And then when we do all that, we're just going to end up with whatever our final number is. So we're going to work with some graphs and some applications of this model starting on, I don't even know what day it is today, starting on Friday. Okay? Have a good one. We'll see you then.